The grounding electrode conductor or GC return loop request could be based on a few reasons. Firstly, local code interpretation. Some jurisdictions may have local amendments to the National Electrical Code (NEC) that require a return loop GC for grounding systems. Secondly, enhanced grounding continuity. By creating a complete loop, a GEC provides two paths for current to flow in the event of a fault or surge. This enhances the overall grounding continuity and reduces the risk of damage to equipment. Thirdly, inspector discretion. Inspectors may request a return loop GEC based on their experience and judgment. They may believe it provides additional safety and reliability. Fourthly, utilities requirements. Some utility companies may have specific requirements for grounding systems, including the use of a return loop GEC. This may be due to the nature of their electrical distribution system or the specific hazards that may be present in the installation area. The National Electrical Code (NEC) does not explicitly require a return loop GEC. However, it does state in section 250.50 that the grounding electrode conductor shall be installed without splice or joint. This implies that a single unbroken conductor should be used for the GEC. In general, it is recommended to follow the requirements of the local code and the utility company when installing a grounding system. If an inspector requests a return loop GEC, it is advisable to comply with their request, even if it is not explicitly required by the NEC. However, if you have concerns about the NEC compliance or safety of the request, it is important to discuss them with the inspector or a qualified electrician. It is important to understand the purpose of a grounding electrode system and the role of the grounding electrode conductor. The grounding electrode system provides a connection to the earth, which serves as a reference point for electrical systems. This connection helps to stabilize voltage and provide a path for fault current to flow back to the source, allowing overcurrent protection devices to operate and clear the fault. The grounding electrode conductor connects the grounding electrode system to the electrical system, typically at the service equipment or the main panel. It is essential that the GEC is properly sized and installed to ensure effective grounding. Now let's delve into the specifics of the NEC requirements related to grounding electrode conductors. Article 250 of the NEC covers grounding and bonding requirements, including those for grounding electrode conductors. Section 250.66 specifies the sizing requirements for GEC based on the size of the service entrance conductors. The GEC must be sized no smaller than specified in Table 250.66 based on the size of the service entrance conductors. For example, if the service entrance conductors are 2/0 American wire gauge copper, the GEC must be at least number 4 American wire gauge copper. It's important to note that the size of the GEC is based on the size of the service entrance conductors, not the size of the grounding electrodes. Section 250.64 covers the installation requirements for grounding electrode conductors. It states that the GEC must be installed in a continuous length without splices or joint, except as permitted in 250.64c. This requirement is intended to ensure a low impedance path to ground. Section 250.64c allows for the use of irreversible compression connectors listed for the purpose or exothermic welding to splice or join GEC. However, these methods should only be used when necessary, and the connection must be made in a manner that ensures a permanent and reliable connection. Section 250.53c covers the requirements for grounding electrode systems and specifies the types of grounding electrodes that are permitted. These include metal underground water pipes, metal frames of buildings, concrete encased electrodes, ground rings, and rod and pipe electrodes. When using rod or pipe electrodes, at least 2 electrodes must be installed and spaced at least 6 feet apart. This is to ensure that the grounding system provides a low impedance path to ground, even if one of the electrodes becomes compromised. Section 250.70 covers the methods of grounding electrode connection. It requires that the connection between the grounding electrode conductor and the grounding electrode be made using listed connectors or exothermic welding. The connection must be accessible and made in a manner that ensures a permanent and reliable connection. Now let's discuss the concept of impedance in grounding systems. Impedance is the total opposition to current flow in an alternating current circuit. It is the combination of resistance and reactance. In grounding systems, low impedance is crucial for effective grounding. A low impedance grounding system provides a path for fault current to flow back to the source quickly, allowing overcurrent protection devices to operate and clear the fault. High impedance in a grounding system can impede the flow of fault current, which can lead to elevated voltage levels and increased risk of equipment damage or electric shock. Several factors can contribute to high impedance in a grounding system, including undersized grounding conductors, loose connections, and corroded grounding electrodes. To minimize impedance in grounding systems, it is important to use properly sized grounding conductors, ensure tight and corrosion-resistant connections, and regularly inspect and maintain the grounding system. Now, let's explore the different types of grounding electrodes commonly used in electrical systems. Firstly, metal underground water pipe. A metal underground water pipe can be used as a grounding electrode if it is in direct contact with the earth for at least 10 feet. The water pipe must be electrically continuous and free of insulated couplings or sections. The connection to the water pipe must be made within 5 feet of the point where the water pipe enters the building. Secondly, metal frame of the building. The metal frame of a building can be used as a grounding electrode if it is effectively grounded and electrically continuous. The metal frame must be connected to the grounding electrode conductor at multiple points to ensure a low impedance path to ground. Thirdly, concrete encased electrode. A concrete encased electrode, also known as a U for ground, is a grounding electrode that is encased in concrete. It typically consists of at least 20 feet of bare copper conductor that is encased in at least 2 inches of concrete. The concrete encased electrode must be located within the bottom of a concrete foundation or footing that is in direct contact with the earth. Fourthly, ground ring. A ground ring is a grounding electrode that encircles a building or structure. It typically consists of a bare copper conductor that is buried at least 30 inches below the surface of the earth. The ground ring must be at least 20 feet in length and must be connected to the grounding electrode conductor at multiple points. Fifthly, rod and pipe electrodes. Rod and pipe electrodes are grounding electrodes that are driven into the earth. They typically consist of steel or copper rods or pipes that are at least 8 feet in length. The electrodes must be driven into the earth to a depth of at least 8 feet, and at least 2 electrodes must be installed and spaced at least 6 feet apart. Now let's delve into the importance of proper grounding electrode selection and installation. The selection of the appropriate grounding electrode depends on several factors, including soil conditions, availability of grounding electrodes, and local code requirements. Soil conditions can significantly impact the effectiveness of a grounding electrode. Soil resistivity is a measure of the soil's resistance to the flow of electrical current. Low soil resistivity is desirable for effective grounding as it allows current to flow more easily through the earth. Soil resistivity can vary depending on factors such as moisture content, temperature, and mineral composition. In areas with high soil resistivity, it may be necessary to use multiple grounding electrodes or to enhance the soil with ground-enhancing materials to achieve effective grounding. The installation of grounding electrodes must be performed in accordance with the NEC and local code requirements. The electrodes must be installed in a manner that ensures good contact with the earth and provides a low impedance path to ground. Connections to the grounding electrodes must be made using listed connectors or exothermic welding, and the connections must be accessible and made in a manner that ensures a permanent and reliable connection. Now let's discuss the role of bonding in electrical systems. Bonding is the process of connecting all metal parts of an electrical system together to create a low impedance path for fault current to flow. Bonding is essential for electrical safety as it helps to minimize voltage differences between metal parts and reduces the risk of electric shock. Article 250 of the NEC covers bonding requirements, including those for equipment grounding conductors, metal water pipes, and metal building frames. Equipment grounding conductors are used to connect the metal parts of electrical equipment to the grounding system. They provide a path for fault current to flow back to the source, allowing overcurrent protection devices to operate and clear the fault. Metal water pipes and metal building frames must be bonded to the grounding system to ensure that they are at the same electrical potential as the earth. This helps to prevent voltage differences between these metal parts and reduces the risk of electric shock. Now let's explore the concept of ground fault circuit interrupters, or GFCIs. GFCIs are devices that are designed to protect people from electric shock. They work by monitoring the current flowing in a circuit and detecting any imbalances that may indicate a ground fault. A ground fault occurs when current flows through an unintended path to ground, such as through a person's body. When a GFCI detects a ground fault, it quickly interrupts the flow of current, typically within milliseconds, which can prevent serious injury or death. GFCIs are required in many locations in homes and businesses, including bathrooms, kitchens, and outdoor areas. They are also required for portable generators and construction sites. Now, let's discuss the importance of regular inspection and maintenance of grounding systems. Grounding systems should be inspected and tested regularly to ensure that they are functioning properly. Inspection should include a visual examination of grounding conductors, connections, and electrodes to identify any signs of damage or corrosion. Testing should include measuring the impedance of the grounding system to ensure that it is within acceptable limits. Any deficiencies identified during inspection or testing should be corrected promptly to maintain the effectiveness of the grounding system. Now let's explore some common grounding mistakes to avoid. One common mistake is using undersized grounding conductors. Grounding conductors must be sized in accordance with the NEC to ensure that they can safely carry fault current. Another common mistake is making improper connections to grounding electrodes. Connections to grounding electrodes must be made using listed connectors or exothermic welding, and the connections must be accessible and made in a manner that ensures a permanent and reliable connection. Another common mistake is neglecting to bond metal water pipes and metal building frames to the grounding system. Metal water pipes and metal building frames must be bonded to the grounding system to ensure that they are at the same electrical potential as the earth. Another common mistake is failing to install GFCIs in required locations. GFCIs are required in many locations in homes and businesses to protect people from electric shock. Now let's discuss some advanced grounding techniques. One advanced grounding technique is the use of ground-enhancing materials. Ground-enhancing materials are substances that are designed to improve the conductivity of the soil and reduce soil resistivity. These materials can be used to enhance the effectiveness of grounding electrodes in areas with high soil resistivity. Another advanced grounding technique is the use of isolated grounding systems. Isolated grounding systems are used in sensitive electronic equipment to minimize noise and interference. In an isolated grounding system, the grounding conductor is isolated from the normal equipment grounding conductor and is connected directly to the grounding electrode. Now let's explore the future of grounding technology. Grounding technology is constantly evolving, with new materials and techniques being developed to improve the effectiveness and reliability of grounding systems. One emerging trend is the use of nanotechnology in grounding systems. Nanomaterials have unique properties that can enhance the conductivity and corrosion resistance of grounding conductors and electrodes. Another emerging trend is the use of smart grounding systems. Smart grounding systems use sensors and monitoring devices to continuously monitor the performance of the grounding system and detect any potential problems. In conclusion, understanding grounding electrode conductor requirements is essential for ensuring electrical safety and compliance with the National Electrical Code (NEC). While a return loop GEC may not be explicitly required by the NEC, local codes, utility requirements, or inspector discretion may necessitate it. Always prioritize compliance with local regulations and consult with qualified professionals when in doubt. By following best practices for grounding electrode selection, installation, and maintenance, you can create a safe and reliable electrical system. Remember to consider factors such as soil conditions, impedance, bonding, and the use of GFCIs to ensure optimal grounding performance. Additionally, staying informed about advanced grounding techniques and emerging technologies can further enhance your understanding and application of grounding principles.